Welcome back, everybody, to my shelter in place. Such a nice room here I've been stuck in for the past month or so, can't complain about that. It's a nice sunny day right here. Got some sun going on this Monday, April 20th. And you've made it. That's right, you've made it. We've finished chapter 9. So now we've done 9 full chapters. If you were here the first 2 weeks of the semester, we did propositional logic as well. So, hey, we've just busted through a whole bunch of material. And it can seem like a lot. It can feel like, hey, what did I actually learn here? And the reality is that there's been a lot of information, okay? So a lot of people, if they're not digging deep, they're not learning as much as you guys. So hopefully you're still digging deep and doing your best and just doing the best you can every single day. That's really what it's all about. I know it can be tough sometimes with internet connectivity issues, sharing things with your siblings. So definitely reflect on where you are and just try to do your best. And reach out to me too. I'm willing to talk with you about anything if you think you're having trouble and having trouble keeping up. Really what this is about over the next several weeks is just to give you as good as an education as you can get. Before the end of the semester. And so I think I've made that available so that you can get to well beyond even what the typical geometry student usually gets to. But the key thing is that I don't want to put too much pressure on you, but I want you to be able to see a lot of problems because I think you'll feel better down the line if you know how to do a lot of the problems. And regardless, I think you're going to be in good shape. Okay, so areas of plane figures was chapter 9. We haven't done solids yet, right? So solids are three-dimensional figures. So how much of space would get taken up by, say, I don't know, this notebook? This is kind of a prism. What else do we have here? I don't know. This is kind of a cylinder. So stuff like that will be coming up in chapter 10. I don't know exactly when we're going to do chapter 10. Usually I do chapter 11 and chapter 12 first because I think those are a little bit more different. Chapter 11 is coordinate geometry, otherwise known as algebraic geometry, so it's got a good algebra tie-in. And chapter 12 is transformations. So transformations on the XY coordinate axis. So it kind of goes with chapter 11, coordinate geometry. Okay, so we're probably going to do those first and then get back to the stuff here that we're doing with areas. Okay, because chapter 10 isn't just solids, how much solids take up of in a region of space, and that's known as volume, of course. It's also the areas of solids, of three-dimensional solids. So usually that gets referred to as the surface area of a particular prism like this, or of a cylinder, or of a... That pig's a cylinder over there. What else do I have in this room? So that'll be coming up. Okay, but you made it. You've done this in chapter 9, and this is just some review and practice. I'm mostly just going to tell you what you can work on to kind of make sure you solidify what you know in chapter 9 after this. Okay, so let's go ahead and get started. All right, and instead of taking you back through all those lecture sites, because again, you have all the lecture sites for chapter 9, I would probably just give them a once through. Go through and just re-familiarize yourself. Is that a word? I don't know if it's a word. Re-familiarize yourself with the way everything got proven in chapter 9. It's probably the best way to remember all of the formulas and where they all come from. Because again, as I said, the very first day we did chapter 9, chapter 9 isn't about just, hey, calculating area, because you did a lot of calculating of area in middle school and before. What it is in geometry, 9th and 10th grade, is figuring out how those formulas got derived. Where did they come from? And they all came from one place. There was really only one major assumption we needed to make at the beginning of this unit, and that was the square postulate right here. So we might as well define area, the amount of the plane that would be bounded by a particular figure. We got to start with the square, because everything can be broken down into how many unit squares can be sliced and diced up to fit any given shape. And those could be polygons, or they could be non-polygons. They could be curved figures that are bounding particular areas of the plane. So then after that, right, we did found the area formula for a rectangle. That was that fancy one where, well, we had to start with something that had, for instance, a base and a height to it. Could have called them the other way around. Probably would have made more sense. And then we made a square out of it, right? So we used the square postulate by being very clever in proving this one. Any rectangle, you can create a larger square. You can complete a square A lot of you guys in Algebra 1 probably studying completing the square by now, I hope, where you can create a b plus h height and an h plus b width over here is the way I tried to do this one. So this should have been probably a little bit shorter here. It'd be more like a square. All right, so this whole thing here would be b squared plus 2bh plus h squared in terms of its whole area. And it would also be made up by its component parts as well. So area as a product would be what I just told you. Area as a sum would be, well, this would be the area we were trying to find. This would be another one of the areas we were trying to find here. And then this would be h squared, and this would be b squared. So remember that one. The way that this got derived here is that we have these two a's right here, and I'm going to do this with a lot less simplification. But remember, so this whole thing, this square that we completed out of this original area that we were trying to derive a formula for this original rectangle, is we can have it as a product, which again is b squared. B times b is b squared, and h times h is h squared. But then h times b is hb, and h times b is hb. So you would have two hb's, or two bh's. Two bh's here. So two bh's would be that middle term of the trinomial. All right, let's just do it real quick up here. All right, h plus b times by h plus b, area as a product, would be h squared plus, here's a bh, and then here's another bh if we're foiling this here, or using a generic rectangle to multiply this out. I'm just going to do it in my head and go a little bit faster. Okay, b squared. Right, so remember here, if we're trying to do it as a product, here's it as a sum. Our h squareds and b squareds would cancel out, right? Would cancel out. So 2a equals 2bh, and then a equals bh. So this sort of logic here is just understanding that these formulas come from someplace. I'm not sure if you're ever going to really have to explain this, unless you become a geometry teacher, explain how to derive the formula for an area of a rectangle. But again, it all comes from the square and the square postulate. Parallelogram extended from there, right? That was the one where we have a rectangle, right? We would say that this, if we dropped an altitude here of a parallelogram, and we dropped a corresponding altitude here, then this would form a congruent triangle to this right here. So that means we could use the area of this rectangle, the one right before it, to approximate the area of the whole parallelogram, because this area of this rectangle here would have to be the same as the area of the parallelogram. So area addition postulate would be necessary there to subtract and get the work done. Triangle, okay, triangle, remember, is just half of a parallelogram. So any triangle, right? So if we're trying to get the area of this triangle right here, well, we can just double it and make it a parallelogram. So that would prove that it would just be half of the parallelogram formula. Rhombus was another good one. That one is an important corollary just to make you remember that it oddly comes up in a lot of standardized test questions, but the rhombus is the special one, the key thing, and it comes up again and again. It actually this one was hard for me to remember in high school, but the diagonals of a rhombus are perpendicular to one another. So we can take, and they also bisect each other because it's a parallelogram. So we can take this area here would be D1 if the whole thing is D1, and the height of this would be 1/2 D2 because the diagonals bisect each other. So the area of this top triangle would be 1/4 D1 times D2 because 1/2 base, so 1/2 D1 times height, which is 1/2 D2. So this would be 1/4 D1 D2. So the bottom also would be 1/4 D1 D2. So the two triangles here would have the same area, which would be 1/4 D1 D2. So simply adding them together to get the combined region. These are non-overlapping regions of a polygon. We just got to add those non-overlapping regions to get the total area, and that would be this formula. Trapezoid. That was a nice proof. I like that proof a lot. So this is dealing with a trapezoid. And that, of course, just simply comes from the triangle formula. These would have the same altitudes. Altitude would be over here. This would be h. Okay, and then so you would find a one triangle, which is 1/2 B1H and 1/2 B2H, and you just have to add them together. So that's where that formula comes from. Right? There's the median. So the median is the average of the two bases. So if we take our height and multiply it by the median, we would get the area of a trapezoid. B1 plus B2 over 2 is the formula for the median of a trapezoid. And regular polygon, that one we've spent a couple classes on now, so I'm not going to spend too much time on that, but that would just be area equals 1/2 the apothem times by the perimeter. Every single regular polygon is made up of, every n-sided, let's put it this way, n-sided regular polygon is made up of n triangles. N triangles where they have a given side length. We just need to take that given side length and multiply it by how many sides they have, so by n, to get the perimeter. So you take the perimeter and then multiply it by the apothem and then divide by 2. That will give you the area of a regular polygon. Another way you can think about it is that each of those triangles would have the area 1/2 times by AS, right? 1/2 times by AS, because the side length would be the base of a triangle, and the apothem is the altitude that goes from the center of that regular polygon to the side of the triangle. So 1/2 AS, and then you would have to multiply by n, right, number of sides to get to the perimeter, right? NS is perimeter. So I'm going to write that other formula that we have for area of a regular polygon right here. Area equals 1/2 ANS. Last formulas here, we did a second ago. This one was pretty easy. So circumference is 2 pi times longer than what the radius is. Okay, so the diameter of any given circle, its circumference going around the circle, it would be about 3.14 times longer to go around a circle than to go across the circle. So thinking of that equator problem we had recently, a couple days ago, to go through the center of the Earth to the other side of the Earth, through the center of the Earth, that is quite a bit shorter than going around the Earth and flying, for instance, circumnavigating the globe on a plane, okay, would be going around the circumference of the great circle of Earth is 3.14 times longer, approximately, right? Pi times longer than going through the center of the Earth. So this is why this pi thing is so special here. So if you have the radius, you need to double it, get the diameter, and then multiply by pi. That tells you the circumference. Area is the one where we see squaring, okay? So a lot of people might forget which one's which. What goes with circumference? Which one goes with area? Remember that area of the units are squared. So that means at some point you're usually multiplying one of the dimensions by another one of the dimensions. Look at this here. In all the area formulas, we're multiplying 2 dimensions to one another. 2 dimensions to one another. Here we're combining one of the dimensions here and multiplying to another dimension. So 2 dimensions together. And these are 2 different dimensions here even for the square. This is one side length times another side length going another direction. So the radius here, instead of it being 2 distinct dimensions that we know about, we're just multiplying the radius to itself and then multiplying by pi, and then that gives us the area of a circle formula. Area of a sector is just going to be the ratio of how big that sector is to the circle. So you need to just take the area of a circle formula, find the area of the circle, and find what fraction of the circle would be occupied by that center. It's as simple as that. So a 60-degree sector would take up 1/6 of the area of a circle. Seems obvious? Oh, those questions are actually kind of hard for some people. So it's nice if you think the logic makes sense, then the logic does work. So here's the formula for area of a sector, and then here's the formula for the length of an arc. Remember, we have arcs that are defined by their measure, but a 60-degree arc in one circle would be different than the 60-degree arc in any other circle unless that circle is congruent to the circle you're talking about. So a 60-degree arc says really not much about how long that arc is, what its length is, what its distance. If you laid it out as a straight line, it says very little about its distance. But if we knew how big the radius were of the circle, and we knew how much of the circle is taken up by that arc, so if we knew the measure of the arc, say it's 180 degrees, right? We know it's a semicircle, 180 degrees. You just need to divide that by 360 to figure out the ratio of the circle taken out by that arc. So 180 over 360 is 1/2. So you would just pi r would basically be the length of a semicircle. It would just be pi r. Last thing here, and don't think these are super straightforward here too. If the scale factor of two similar figures is a to b, then the ratio of perimeters is a to b. So they're talking about specifically similar figures. So perimeters is still a to b. You're doubling the side lengths. That's just going to double the perimeter. So if it's a square, for instance, and one side is 8, and another side is 8, and then all of a sudden it's a 4-sided square. So 4 plus 4 would be 8, plus 4 plus 4 would be 16. So in the original square, if it were 8, it would be 32, because 8 times 4 is 32. So your perimeters would also be getting twice as small in that situation. So the ratio of perimeters would still be 2 to 1, because going from an 8-sided square to a 4-sided square is a 2 to 1 change. Areas is different, right? Areas is a change you have to square, because the area formulas, again, you're multiplying one dimension by another dimension. So if both dimensions are changing, it's changing by kind of a quadratic factor here. So if you're going from an 8-sided square to a 4-sided square, making it a little bit harder when it gets smaller, it gets harder, your area is going to change from 64 to 16. So if you're changing by a scale factor of 1/2, your areas will get 1/4 smaller, right? 64 times 1/4 would be 16. So keep that in mind. And this is not to be confused with, say, if one side of something is different than another side of a different thing. You need to actually inspect to see, are they similar figures? Do they actually have all the side lengths in a proportion together? Or is just one of the side lengths really different in one particular way, but their altitudes are the same? Or one of the other features is the same that you use to calculate area. And then in that instance, you can't follow this. The ratio of areas is the square-to-square ratio of the scale factor. Okay, so just be careful on that. Those are some common ways they can lead you astray. But if you're on the lookout for it, you know it now here in 9th grade, you're in good shape. Here's your homework. That was my little talk through everything. I figured, why not just talk about the whole thing? Because, hey, we've been on this chapter for over a month now at this point. This is usually like a couple-week chapter. You can knock it out and move on to chapter 11 after this. Remember, I think we're going to skip chapter 10, go straight to coordinate geometry, and then wrap up with transformations, or we'll also do some volume at the end of the year. Volume is a pretty good unit, I think, because we got some worksheets for those. Those are kind of more independent investigation, less lectures, fewer videos you'll have to watch that are kind of structured like this, going through lecture slides. Okay, so here is your review for this on this beautiful Friday. You got your chapter test, number 1 through 18 all, and then you have mixed review, page 420, number 2 through 18 all. Best of luck. Talk to you guys later. Bye.